Hey everyone, in this video I want to do a 3D problem, and I want to work through this problem, and I want to do a little bit of velocity, and I want to show you what happens to the complexity of the problem when you start working with actual 3D problems. Now, most of the problems we're going to do this semester are not 3D, but I always think it's important to let you know where the field is going. What do more difficult problems look like? So the important thing you should take out of this video is that the approach is actually exactly the same. We're going to do the same position, orientation. This problem has no constraints. If it did, we would do those as well. But linear velocity, angular velocity is the exact same procedure regardless of the problem. All right. So what we want out of this problem. Well, first of all, let's put some points on it, and let's talk about this problem. So here's our non-moving inertial point in. This pin joint is going to be point A, and then there is a point at the end of the second pendulum, and that is B. What we want is we want omega into B, and we want VB. Now, how is this system moving? Well, this vertical base, this column, this is immobile, so this is just ground, but there is a rotation around that vertical base. So we can imagine my body then, like my chest, I could be this vertical base, and I'm just doing a simple rotation, right? I'm doing a simple rotation around a z-axis, so I'm just turning like this. So this body A then, this body A is spinning, and if you were looking top down on it, it would look just like a pendulum. For example, if my body is the vertical column, this would be like if I put my arm straight out and I just rotated like this. So what frames do we need to put on here? Well, we know there's the non-moving inertial frame. So Zn is pointed up, so we're going to do a rotation around a shared z-axis. Here's x, here's y, and that's xn, yn. Okay. Next, we have body A. Body A is spinning. We need the position vector from point N to point A, and let's make that position vector be along the xa axis. Okay. If that's the xa, then ZA is pointed up, right? Because the Z's are aligned. Simple rotation from A to N. And just for fun, where's Y? Y is currently pointing off like this, right? It looks a lot like our inertial frame. So the xa goes the length of this thing into A. What are we going to do now for B frame? Up until now, all the problems we've done, we've used the x-axis for our position vector. So into A to B, B to C, we've used x repeatedly. The problem is this rotation between A and B is around this axis, right? It's straight out now, and then there's a pin joint there, and then this pendulum is spinning this way. It's not spinning around the same shared Z. Now it's rotating around this x-axis that's coming right through the length of it. So in the example of my arm, it would be akin to me bending my arm at the elbow. So now I can rotate my arm, and then I can also spin at this other joint. So this second pendulum is now spinning in this direction. So that means that this is x hat A also, and it's also x hat B. So in this problem, we first do a simple rotation around a shared z-axis, and then we need to do a simple rotation around a shared x-axis. So if this is the x-axis, let's define the length now as the yb axis. And then the zb would be coming off of it like that. There's zb. Okay, let's turn this into some vectors, and what can we write down off of this? First of all, the position vectors, P into A. None of these lengths change. The only thing that changes is the directions. They're just spinning. So we could say L1 x at A, and then P A to B. This is going to be L2 x, nope, not x, L2 YB. There it is. Okay. How do we define orientations? Well, simple rotation on A, so we've done this many times now. We know that XA is cosine theta xn plus sine theta, this is theta 1, yn. So negative sine theta 1 xn, sine theta 1 cosine. There we go. Cosine theta 1 yn. And ZA equals Zn. All right, so write that one down. Make sure you do a diagram with it. It's the same thing we always do. Next, let's define the rotation of the B frame. So we've talked a lot about using relative or absolute angles. In this problem, you have to use relative. Have to use relative. Why have to? Because consider there's this first axis that's spinning, and then we're spinning around this shared x. You cannot get from the N frame to the B frame with a simple rotation, with one simple rotation. You can't do it. So in order to define it, we need to use relative angles. So which kind of simple rotation are we going to do? We're going to use a relative angle going from A frame to B frame, and we're going to rotate around this shared x axis. So I did this in another video where I talked about how to rotate about different axes. So if you're rotating around a shared x, then the plane that is rotating is the YZ plane. So this is Y and Z. And since we're using relative angles, we need to go from the A frame, so YAZA, to YB ZB. And the angle between them, that angle is theta 2. Next, we need to define that rotation. Again, we're using relative angles. So this is the rotation, A to B, and then we have XB equals YB equals ZB equals. Okay, so again, this was all in that other video, but we can do it now. Shared axis is X, so XB equals XA. Next, the YB is the location where X usually is, so it's cosine between Y's and then it's sine between Z's. So this is cosine, we're dealing with theta 2 now. Cosine theta 2 YA plus sine theta 2 ZA. And the Z-axis is where the Y normally is. We can see that it's going to be cosine between the Z's, and it's going to be negative sine with respect to the Y. So this is negative sine theta 2 YA plus cosine theta 2 ZA. There we go. So there's our rotation now for from A to B. It's a relative angle around this this moving XA axis. Okay. So we've got all of this now in our notes. This defines the rotation of those two frames. We can write down location description for body A and body B. Next, let's talk about the generalized coordinates. So there's no lengths changing here. There were two generalized coordinates. It's theta 1 and theta 2. Now, there are no constraints on this problem. And there are 2 degrees of freedom. And if you recall, what degree of freedom really means is that these coordinates are independent. So consider, could we hold the base in place and not allow any rotation at that first joint? And then could we just spin the second joint? Yeah. We could hold the second one fixed. We could put a lock on this joint, and then we could freely spin the first joint, right? We could freely spin both joints, and they don't affect each other. The motion of B is obviously going to end up being a function of both of them, right? We're going to see that in the math, but they're not affecting each other, the two angles, theta 1 and theta 2. So they're both independent. So 2 degrees of freedom. Next. Well, I recommend doing angular velocity first. Again, just because you can do it from observation. So the first one is omega into A, and this is around a shared z-axis, and the angle there was theta 1. So this is theta 1 dot, and we could say ZA, we could also write it as ZN. It's the same thing. Next, recall that we're using relative angles. So we define rotations from A to B, which means the angular velocity is A to B. What angle did we choose? We did theta 2. So this is theta 2 dot. And then what axis are we rotating around? We're rotating around these, and they're the same. So we can write it as XA or XB. It doesn't matter. But there is your angular velocity. Now, we're going to take derivatives of position vectors in a bit, and we're going to have to use transport theorem. And when you use transport theorem, you use the total angular velocity every time. So this is not the total angular velocity. This is just a little piece of the B frame's total. So let's wrote kind of big, so I'm just going to erase it. Omega into B, right? The total angular velocity is equal to omega into A plus omega A to B. And you can just add these two. So this is theta 1 dot ZA plus theta 2 dot. And we could do, we could write this one as XA if we want. I could write it as XA. I could also write it as XB. The fact that the first term is in the A frame doesn't mean that the rest of these have to be in the A frame. It's kind of like we saw with position vectors. You could have a piece of the position vector in A, and a piece in B, and a piece in C, and that's valid. I'm just going to leave it as this. So theta 1 dot ZA, theta 2 dot XA. All right, so we've got angular velocities for these. What's next? Linear velocity. Okay, so VA, let's start with VA. We know the definition of linear velocities. We know that this is ddt of the position vector. So this is ddt then of L1XA. We know that we could do a product rule expansion on this. We know that L1 is a constant, so the derivative of L1 is 0. So VA is going to shorten down to L1 ddt of XA. Now, anytime you see ddt of a moving frame, you can do transport theorem. I'm going to replace this term with omega NA cross, and there's some vector here. What are we crossing it with? Well, where did this come from? This came from ddt of L1 x at A. So I'm going to bring in L1 x at A. And what is omega into A? We said that omega into A was theta 1 dot z hat A. All right, so what is VA? VA is theta 1 dot ZA cross L1 x at A. Multiply the scalars. L1 theta 1 dot, and then it's Z cross X, and Z cross X is positive Y. So there we are. VA is L1 theta 1 dot Y hat A, which looks like all the previous problems we've done before, right? Okay, let's look at what happens on point B. All right, so this time we want VB. We know that this is ddt of P into B. We know that this, we could actually break this up if we wanted to. We could say that this is ddt of P in A plus PA to B, right? And we could distribute the ddt. So this is ddt of P in A plus ddt P and B, sorry, PA to B. Okay, so what's this first piece? We've actually done this already. We just did. This is VA. So let's rewrite this whole thing. So VB is equal to VA plus ddt of PA to B. All right. So an interesting thing you can do if you want to dig into the nomenclature, we could rewrite this portion. I could say VB is equal to VA plus VA to B. So if you're taking the derivative of the position vector A to B, you get the velocity from A to B. This is a relative velocity. We're going to do some more problems with relative velocities, but you can imagine that if you're in your car driving and you're going a certain speed and you look into the lane next to you and there's another car driving and you're both going in the same direction and that car is going 10 miles faster than you, 10 miles an hour faster, then from your perspective, the car is only going 10 miles per hour. It's the change in the velocity of two bodies, or 2 points, in this case, point A and point B, the velocity between 2 points, and those points can both be moving. If you look to the other side of the interstate and you see cars going in the other direction, and if you're going 60 and they're going 60 in the other direction, then from your perspective, they're going 120. So that would be this relative velocity term. So we know what VA is. We've already sorted that out. L1 theta 1 dot y hat A. You can directly just bring that in. So really in this problem, what we need to work out is we need to work out this relative velocity A to B. So let's do that. And also as a heads up, suppose that you were doing this on a homework or an exam and you wrote this term on bottom and you've already defined VA, and then you come back and you just define VAB, boom, you're done. You can, if you want, put it all together and clean it up, make it look nice. But just defining things kind of piecemeal like this, where you say, all right, here's a piece of it, and here's a piece, and there's the other piece, that's also acceptable. Okay, so what we want now is we want VAB. So VAB is ddt of P A to B, and we know that that is going to be ddt of L2 YB. Okay, we want to take ddt of this. We can do a product rule expansion. We know that ddt of L2 is 0 because L2 is a constant. We're going to be left with VAB is L2 ddt of YB. Now, what do? Whenever we see ddt of a moving frame, we can replace this term using transport theorem. So VAB is going to equal transport theorem every time. It's omega cross something. So the omega in this case, we're taking the derivative of B frame. We need the angular velocity from N to B. It's always the total. If this was the J frame, we would take omega N to J. What do we cross? Well, where does this come from? It comes from this position vector. I'm going to take this position vector, I'm going to bring it down. So L2 YB. Okay. So we just have to resolve this cross product and we get the answer. What was omega N to B? We said this was theta 1 dot ZA plus theta 2 dot, this was XA. And remember that XA and XB, these were the same things. I'm just going to bring this position vector down so we have it. All right. Can we resolve this cross product? Well, yeah, I mean, it's just a math operation. We can always resolve it, but there's a problem the way I have written it. This is ZA, and this is XA, and this is YB. They're in different frames, and you can't do the cross product on two vectors in two different frames. What that means is we have to either take the angular velocity and go from A frame on both of these quantities into the B frame, or we need to take this position vector and go from the B frame into the A frame. Either way will work, and either way, if you do it carefully and correctly, either way will give you the correct answer. So let's take this second piece. Let's take this position vector, and let's put the position vector in the A frame. And we can do that quickly because, again, we've already defined the rotations of these, right? Remember we had on the second rotation, it was rotating about shared X. When you rotate about shared X, it's Y and Z like that. So we had written down earlier that YB was equal to, this is going to be cosine theta 2 YA plus sine theta 2 ZA. That was the definition of the rotation that we came up with. So let's rewrite this cross product then using that. We had VA to B, this is equal to, we're going to say theta 1 dot ZA, theta 2 dot XA, and then this is going to be crossed. The length is L2, and then it's cross cosine theta 2 YA sine theta 2 ZA. So here's the cross product, and we have converted this YB into the A frame. So let's talk about now resolving this thing. You can of course resolve the cross product any way you like. I prefer to just kind of do a multiplication and then just look at the axes. And you know, if you need to, you go back and you write down what these definitions were. X cross Y is Z, Y cross Z is X, and Z cross X is Y. Right. Okay. So what does this come out to be? VAB. We can do just like a FOIL expansion on this, right? This is like A plus B multiplied by C plus D. So let's just take the first term and you multiply against the first term. Let's multiply the scalars. So we have L2 cosine theta 2, right? Multiplied by theta 1 dot. And then this is going to be Z cross Y. Okay, I've got Y cross Z. So Z cross Y, if Y cross Z is X, then Z cross Y is negative X. So this is negative X at A. There's our first term. The second term, so we would have theta 1 dot ZA cross L2 sine theta 2 ZA. Okay, but look at it, notice how it's ZA cross ZA in this case. And we don't have anything over here on these definitions. Recall that for dot products, if you do Z cross Z, you get 1. For cross products, Z cross Z is 0. And if you go back and recall what these operations actually mean, dot product is projection, cross product returns the vector that is perpendicular to the input. So if your inputs are the two blues, black is perpendicular to them. And if you reverse the order of the inputs, you just get the negative. You get the angle in the other direction that's perpendicular. So if you have two of the same, then that's two parallel vectors, and there are infinitely many vectors that are perpendicular to both of them. So this comes out to be 0. So this next component then, if we took the first term here and cross it against the second, it's Z cross Z, so you end up with 0. Next. So the second term now, cross the first term. Let's do our scalars. L2 cosine theta 2 dot, and now it's X cross Y. Okay, we got that one. X cross Y is Z, ZA. And then the last term, this cross the last one, let's multiply the scalars. L2 sine theta 2, and then it's theta 2 dot. And then that is around, well, it's X cross Z, right? So that's going to give us negative y. Okay. So we can take this and we can clean it up a little bit. All right, so VAB, what are we going to get? Let's do a little organization on this. We see that we only have the one theta 1 dot, right? So we can leave this term alone. I'm just going to bring it straight up. And I'm going to bring that negative sign out front. So this is negative L2 cosine, my pins are dying. This is negative L2 cosine theta 2 theta 1 dot XA. Okay, let's just leave that one as is. On this next one, we can actually factor some things out. We could factor out the L2 and the theta 2 dot. So let's say plus L2 theta 2 dot, and then this is multiplied by what? It's multiplied by, let's say, negative sine theta 2 YA, and then plus cosine theta 2 ZA. So I've combined these two, factored out the L2 theta 2 dot. The one on bottom was negative, so negative sine theta 2 YA. The one on top is positive, cosine theta 2 ZA. Good. Now, if you look at this, this is something. If you go back and look at your rotations, the way we define them, this should be, and it is, this is ZB. So what that means is your total velocity, VB. Remember, VB is equal to VA plus VAB, right? We already said what VA was. VA is L1 theta 1 dot YA, and then I'm just going to bring these terms down. Then there's negative L2 cosine theta 2 theta 1 dot, and that's in the XA. Next, there is plus L2 theta 2 dot ZB. And that's the answer. Now, let's ask ourselves, does this make sense? Because it seems kind of messy, right? Here's your diagram, and it's always helpful to be able to go back to the diagram and take these terms and plot them as much as you can, and then just ask yourself, hey, does this make sense? So, first of all, this first term, L1 theta 1 dot YA. Well, L1 theta 1 dot YA, remember that YA is going this way, right? It's perpendicular to the XA. So imagine that you were spinning around the vertical axis. That means point A here is tracking the path of a circle, right? As it goes around, and the instantaneous velocity is perpendicular to that path. So this L1 theta 1 dot YA, this is the velocity of A, and it's just pointing off that way. These next two terms are interesting. This term looks very familiar, L2 theta 2 dot ZB. So if your axis of rotation is like this and you're doing a positive angle, that means you're spinning this way, right? So that means the pendulum, the way it's drawn, it's currently coming up. It's kind of swinging out, which means that point B is tracking the path of a circle around, and the velocity of B is tangent to that path. Well, tangent to the path is Z, right? The Z-axis is the tangent to the path, so that's this term. Now, what is happening here? This term is interesting. Notice that it's theta 1 dot, so we're saying there is some other component now that is a function of theta 1 dot, that is a function of this original spin. So it's a function of this angular velocity theta 1 dot, but it's a function of the current angle theta 2, right? Theta 1 dot cosine theta 2. So what does that mean? Remember that cosine theta 2 is the angle between A frame and B frame. So it defines how B has spun around this axis. So imagine that theta 2 was equal to 0, right? That would make this cosine term be equal to 1, and whatever this is, we're going to get the full magnitude of it. If theta 2 is equal to positive or negative 90, then this goes to 0, and then this term goes to 0, so there's no new contribution. So that means if the angle is 0 between them, then that means YB is aligned with YA. So that means it's actually flat, right? Like this whole thing is in the plane together. From a top-down view, it would look like this. There's point N, and let's say body A, we're looking at it like this, and then if theta 2 was equal to 0, then we would see it like this. We would see the B frame, body B and body A, they would be aligned together. So it's like if I took my elbow and just bent it like this, right? And they're in the same plane. So this was XA, and YA was coming off like that, and ZA is up. So this first term, L1 theta 1 dot YA, hey, that makes sense, right? That's the velocity at this point, and it's tangent to that path. And we've gone out now to this point. Okay, just from a drawing, without even looking at math or anything, if I ask you what's the velocity of that point, and you got a ruler in front of you, you should be able to draw the velocity vector at that point. This is it. You do a straight line to the point, and then you come off of that point 90 degrees. That would be the total velocity of that point if we were spinning around this and this whole thing was in the same frame. So how is this position vector broken up? Well, it's broken into two pieces. And those two pieces, it has a component in YA, and then it has a component in the negative x hat A direction, which is this. So what this term does is it moves us off of this x-axis, directly clean x-axis, and we do the new radius now. And then we say, all right, this point's going to track the path of the circle. And its instantaneous velocity is tangential to the path. That's what this is. So when you do problems in 3D, this is still a tangential velocity, right? It has a similar form as this, but this trig term in it and the negative sign, it might throw you. You should, at least for systems with just a couple of bodies, you should be able to go back to the original drawing and confirm that this makes sense. When the problem gets very difficult, very complex, these terms are going to get nasty, right? They just are. So again, this is why when we do very large problems, especially problems with a lot of bodies, we use software tools. So whatever these expressions come out to be, it can be cosine of this and sine of that, because you have done so many rotations. That is simply the math. And usually we do it, once the system gets really big, beyond 8 to 10 degrees of freedom, we don't actually even have these things solved for explicitly. There's no symbolic math anymore. It's all just done numerically inside of a computer. Okay, so this is the answer. This is the velocity of point B. And we get this interesting behavior, right? This extra tangential term. And this is just what arises when you do three-dimensional problems and you have rotations around several axes. You start getting some more interesting expressions. Okay, I could pull something like this out on an exam. I probably won't, right? But just be aware that I could. So this is what real-world problems look like. So you just have to be rigorous in your approach. Okay. All right, that's it for this problem. I hope it made sense. I hope you're able to follow along. If not, let me or the TA know. We're happy to help out. So best of luck. I'll see you next time.